First things first, the flow graphs we used last week at the Allen Telescope Array, I put them here on the hydrogen line directory. Today, we are going to be covering this scripting directory and also the Python blocks directory. And the main topic for today is how to interface GNU Radio with Python. So I know that probably all of you are familiar with Python. You are working in coding projects which involve Python in some way or form. And one of the major languages in GNU Radio is Python besides C++. So that's the main focus of today. It's because there is some coding, it's slightly more difficult than other tutorials, but I think it's not that difficult anyway. And these days, I'm not even so concerned about difficulty of coding because just if you are aware that these things are possible within GNU Radio, if you don't have strong coding skills, you can use help from Claude or any other LLM. So I think it's like great to know that this is possible so that you can then try on your own or ask the right questions to an LLM if you are using that to help you. So that said, let's get started. I have the scripting thing first. And the goal of this will be to show you how to control GNU Radio from Python. So far, we have been making flow graphs, and that's excellent when we have something which is static and it always runs the same functionality. It might be processing data continuously. For example, the hydrogen line observation we did at the ADA, it was continuously running. Or it might be post-processing a file, so then it just uses a file source block to go through the file and then it finishes. We have also had examples like that. But in any of those cases, it's like all the same processing being applied throughout time. There is nothing which is changing dynamically, really. And also the configuration is part of the flow graph. So that's what's easy to write with flow graphs, but flow graphs are somewhat limited because, for example, you could imagine that maybe depending on some configuration parameters, you want to enable some parts of the flow graph or to disable some other parts of the flow graph or to connect things slightly differently. That might make sense if you are dealing with similar but different signals. You might have to do things differently in each case. I've also spoken, for example, about arrays of antennas. So when we have a large array of antennas, it's just impractical to put a block for each of the antennas. So it would be good to have a for loop. And then something else which really happens always in radio astronomy or SETI is that we have observations. So we run observations, and the observations are usually a sequence of steps. For example, we point the antennas to a calibrator source, we change frequency, we do something, we record some data on the calibrator source, then we go to a target, record some science data, then we might go back to the same calibrator or to a different calibrator. Or if we are doing SETI, we might have also some calibrators to test that the instrument is working. We might have multiple targets, we might have on and off scans. So that looks pretty much like a list of things and like a list of steps which need to be done for each of the things. And that is really difficult to encode in a flow graph. But on the other hand, it is really easy to encode in a programming language such as Python. So that is the thing I'm going to demonstrate. We are going to be using our RTL-SDR sticks, and we are going to be pretending that we are doing an observation with them. Of course, we don't have radio astronomy antennas, but that doesn't matter for the sake of the example. So this flow graph, I'm going to use it as it is because it only has very few things which are new. And so I'm going to save myself the time for to build it from scratch. But I'm going to explain all of it. So there is this RTL-SDR source. It's just the same thing we have been using all the time. I have set the sample rate to 3.2 mega samples per second or megahertz instead of 2.4. For me, it works fine. If it doesn't work on your computer, it might be any issue with drivers or USB or something like that, you can drop it to pin 4. It's not critical for what we are going to do. So we have the RTL SDR source. And then there is this head block, which is new, and it does something really simple. It lets some number of samples go through, in this case 32 million. We will look at where this number comes from. So it's going to let the first 32 million samples pass through, and then it stops. And when it stops, if there's nothing else that it's doing work in the flow graph, it's finished and it finishes. So it makes sense to have this head block whenever we want to make a data collection which has some concrete length. So for example, we could be thinking like we are going to be observing a target for, I don't know, a minute. So how many samples is 1 minute? It depends on the sample rate, but you can calculate and you can use the head block to limit the number of samples and to make the observation length finite. That's the goal. Why is it called head? Maybe some of you are familiar with the Unix command head, which outputs the beginning of a file. So this is the same thing. It outputs the beginning of the data of the input. So that's the reason. Then what else? I have this GUI frequency sync, which is just for testing purposes, and maybe I can start by disabling all of these and testing. So if I enable this and also grab my RTL SDR dongle, which is here, and connect it, I should be able to get a spectrum here, and it will run for some amount of time. The amount of time is calculated here, and it's the sample rate times the duration. And the duration is in a parameter here. So parameter is a new block because so far we have been using the variable block and the Qt GUI entry block, which is used to enter values with a GUI. Parameter give us the option of entering values externally, either from command line arguments or when calling the flow graph from Python code. So this is the way that we are going to pass the duration and other parameters to our observation from a Jupyter notebook, which is the way we are going to run our complete observation. So, okay, what's the problem with this thing? No GUI. Okay, yeah. Something else I need to explain is that there are different modes of flow graphs, or it's actually called generate options. An option is no GUI, which means the flow graph will be console only. It doesn't have any graphical user interface. That's the normal thing if we are running something remotely, or if you are running something from code and we just don't want this GUI window to pop up. However, of course, we cannot have any GUI elements if we choose no GUI. So temporarily, just to test, I need to change this to Qt GUI. And now it should work. So it's running. This should stop in 10 seconds because I have the duration set to 10 seconds. So, okay, it stopped. And whenever we have a GUI flow graph, the GUI remains open after it finishes. But if we have a no GUI flow graph, it's an application that can be run from the command line, for example, and it will just finish and exit. So, okay, so far so good. Then we have this frequency translating FIR filter. And I realize I haven't explained about filtering or decimation, so this is a good moment to explain it. Let's say that we want to select a part of the spectrum. We might only be interested in recording some portion of the spectrum. Maybe our signal of interest is in there. For example, on the Allen telescope array, we were looking at the hydrogen line. That's at a very specific frequency. The bandwidth that we were using was just a few megahertz of frequency, but perhaps our SDR is giving us much more bandwidth than that. So we want to select just the frequency range of interest. So that is usually done with one of these frequency translating FIR filters, which performs 3 operations in sequence. First, it moves whatever center frequency you specify to 0. That's known as down conversion. It's essentially centering things. That's the reason why it's called center frequency. So in this case, whatever is at 800 kilohertz with respect to the center frequency I have on the LSDR source will be shifted to the middle of the spectrum, will be shifted to 0 hertz. So that's the first step. The second step is actually better justified when I explain the third step. So the third step is decimation. We know that the sample rate sets how much bandwidth we have. For example, the sample rate here is 3.2 million samples per second, and that is equivalent, because we are using IQ sampling or complex sampling, to a bandwidth of 3.2 megahertz. If I want something smaller than that, then I can reduce the sample rate by a process which is known as decimation, which is essentially taking 1 in every n samples. For example, here it says decimation 16. That means that we take 1 in every 16 samples. So we would take one sample, we would drop 15 samples, then take the next sample, drop 15 samples, and so on. And because 3.2 megahertz divided by 16 is 50 kilohertz, I believe, we would be left with, or 200 kilohertz, whatever it is, we would be left with a bandwidth of 200 kilohertz at the output of this thing. So that's great, but the issue is that if we are throwing away samples, as I described, then we get into something which is called aliasing, which means that all the frequencies which are outside the range of spectrum which is representable in the output will be folded into the output. And maybe another day I can do a demonstration of this process, but for today, you just need to know that it exists. So the right way to do decimation is first we apply a filter which removes everything which is going to be outside the frequency range that will be present in the output. And this is how we avoid decimation. And then, so that's the second step on this frequency translating FIR filter. And then the third step is the actual decimation, where we don't have this aliasing issue because we have filtered the signals which are going to be not present in the output. So that's what this block does. Essentially, what's going to do here, it's center at 800 kilohertz relative to the center frequency of the SDR. It's going to take a 200 kilohertz slice of spectrum, and 200 comes because 3.2 megahertz divided by 16. And that's going to be the output of this block. We can actually test it. So I think I need to set this back to Qt GUI. So this on the top is actually the output of the frequency translating FIR block. And you can see that it's the same signals here. So it's only 200 kilohertz of spectrum from minus 100 to plus 100. So that would be like this region of the spectrum. We have basically cropped this part of the spectrum. So you can imagine this operation is very frequent in signal processing, because what's happening here is I have a number of broadcast FM stations. I have a station here, I have a station here, and I have a couple other stations here and here. So if I want to select just a single one of them, which is the thing that your card receiver does, for example, then I need to apply this operation to extract only this signal. Okay, any questions at this point? Great, let's move on. So I can disable these two again. I can set this to no GUI. And then I want to record this data. So the data which is at the output of the frequency translating FIR filter, that would be just my single FM station. I'm going to use a SIGMF sync source. In the past, I've used the file source. Sorry, file sync. File source is for playing a file, so file sync. These two blocks are very similar. The only difference is that file sync records a raw file. So we need to remember what is the format of the file, what frequency we were observing, what's the sample rate, any other things that might be important, like, for example, what source we were observing if we were using a telescope. So we need to keep track of all of that manually. There is a standard format for recording raw IQ data plus metadata, and the metadata is recorded in JSON format, so it's human readable, it's very easy to process and edit, and that standard is called SIGMF. We'll take a look later at how SIGMF looks like. So this SIGMF sync is going to record data in SIGMF format. It's called minimal and it's yellow because it only implements the bare minimum of the standard to be functional. So the goal when this was introduced a few years back is that a full-fledged SIGMF sync would appear at some point. And there are actually out of 2 modules which have more featureful SIGMF syncs. But within GNU Radio itself, we still have the SIGMF sync minimal. So that's the reason why it's yellow, because it's deprecated, but it works for what we are going to do. So because it's recording metadata, it needs to know about some parameters, such as the sample rate, which we are supplying here as the original sample rate. So this is the SDR sample rate divided by the decimation. And then the center frequency, which is the RF frequency to which we are tuning the SDR, plus the frequency we are using in the frequency translating FIR filter. And then you can fill in author, description, hardware information, and within SIGMF there are many other metadata variables that can be used. So, okay, this is going to record our IQ data with some metadata. And then we also have some signal processing. This is just an example of signal processing, but it will be useful. So this is going to operate on the whole bandwidth, not on the smaller bandwidth we have selected here. And this is the same as, for example, for the hydrogen line observation. It is recording spectrogram data. So it has an FFT of size 64K points. There's the Blackman window. Then we are taking the magnitude squared because we only care about power. There is this integrate, which is doing integrations. And where is the variable integrations? It is here, so it depends on integration seconds. We are doing 1 second integrations. Here we have 1 second integrations. And then we compute, as always, the number of integrations. It's 49 in this case. So we are doing 1 second integrations. I have this multiply constant block to normalize. So I'm basically taking the average. I do integrate and then I divide by 49 to essentially get the average of these FFTs so that the values I get at the output don't change, don't grow if I increase the number of integrations. This multiply constant block, because these are vectors, we need to give it a list of constants. So that's like each constant for each element in the vector. And you can see it's the same constant in all the components of the 64K point vector. And this is like a simple way to build that vector in Python. If you have like a list of one element and then you multiply by a number, you get a list of that element replicated NFFT times. So little Python trick you might already know about. And this is the vector length, so 64K points. And then what do we do with the spectrum data? We write it to file sync. In this case, this is the plain file sync. There's no SIGMF metadata to accompany it. And we are also writing it to a vector sync. We will take a look at that later on, but for now, the thing you need to know about the vector sync is that it writes the data to memory in such a way that then another application or another part of the same application can grab that data from memory. So this is not writing data to a file, and of course you are limited by how much memory, like RAM memory, you have in the computer. But if you are making recordings of a small amount of data, this vector sync can be useful because you don't need to keep track of files and then remember to delete them when you're done with them. So it's a better way of passing some small amount of data from one part of the application to another one. So essentially what we are going to be doing is to run this observation within a Jupyter notebook, and then we will be reading the data from this vector sync from the Jupyter notebook and using it to make plots. So that's the reason why we have this vector sync. We are also writing to file, but that's like part of the example. I don't think we are going to use the files that are produced here. So, okay, what else is in the flow graph? No, not much. The rest are parameters to set pretty much everything you can imagine. So there is a parameter for the frequency, and then there is this label. It's important to set the types correctly and maybe a default value if you want. So we are, by default, we are tuning to 98 megahertz, which is the frequencies we have seen. Those are FM stations. Then duration, so this is the duration for the recording. I have a default of 10 seconds, but we could change it. Decimation factor, this needs to be an integer. With the block we are using, the decimation needs to be an integer. If you ever need decimation factors which are not integers, there are other blocks that can do it. But with this one, it needs to be an integer. So here we set the type to integer. Then the frequency that we are tuning to with this frequency translating FIR filter block. And finally, file names for the output. So we have the IQ file output. If you are running under Linux and perhaps Mac OS, you can use this file, which is a special device that discards all the input to discard the data and just not write to a file. So that's why I have set it as a default value, but we will be changing that pretty soon. There is also the Spectrum file output, the same. By default, we write to this file, which discards everything. And the rest is the FFT configuration. So this is the flow graph we have, and we also have this import NumPy. Then the thing we can do with the flow graph is we have been executing flow graphs with this play button, but to the left there is generate the flow graph. So if I click on this, it says that it has generated a Python script. And I can go back here to the terminal and check that there is this Python script. So if we run the Python script and run it with help, we can see that for each of the parameters that we have in the flow graph, we get a command line argument to set that parameter. So that's why these are called parameters. They are, or they generate command line parameters. So by running the Python script, we could specify on the command line what's the decimation we want, what's the duration, what's this frequency, what's the file output. For example, I don't know, duration 5 seconds. I can try to run it like so. I think it will fail, and I will show you the reason why it fails. So you can see it's failing, and it's failing because it says I'm trying to open the file /dev/null.sigmf data, and I get a permission denied. And the reason for that is we are using here as a default /dev/null as the IQ file output. Then this IQ file output goes here, but this is a sigmf file sync. So it will create a .sigmf data file to write the IQ data, and it will create a .sigmf meta file to write the metadata. So then, because we are passing this dev null, it's trying to create the corresponding data file, but it's not possible to write here because it's a system directory. So we can fix that. I'm going to use a temporary directory, so maybe ru, for example, and then I can remind myself again what's the right name of this parameter. So IQ file output, and I can say this is temp ru, I don't know, recording, for example. And then we can run, and it should work this time. It will record for 5 seconds a file whose data part is called temp ru recording sigmf data. And we can see that within the ru directory, there is actually, I can list them like so, for example, There is actually a recording.cgmf data, which has, how much is this? 8 megabytes worth of data. And then there is a recording.cgmf meta, which has only 353 bytes of data. So let me show you this CGMF meta file so that you see that it's something really simple. It's a JSON file and it has what's the data type, in this case, complex floating point 32-bit little endian. What's the sample rate, 200 kilosamples per second. What is the CGMF version that produced this? All these metadata fields that I have filled in here, they get placed in here. And then we have captures, which says we only have one segment of data that begins at sample number 0, and the RF frequency corresponding to that segment is 98.8 megahertz. So this is how CGMF looks like, and it's very handy to keep track of metadata from observation. It's only really intended to work for raw IQ data, which is oftentimes not used in radio astronomy. There are some people who are looking into how adapting CGMF for radio astronomy would look like, but to be fair, radio astronomy has been using other formats since before CGMF even existed, like I don't know, guppy format or H5 format. So CGMF is a late newcomer in that sense. So what else can we do with this file? There's an application which is called InSpectrum. InSpectrum, we can Google it. So it's this thing. This is included in Radio Conda. So if you have Radio Conda, you should have InSpectrum, regardless of what platform you're running on. It says it's in Windows, it's included in Radio Conda, but I believe it's included in also in Linux and in Mac OS. If you don't have Radio Conda and you just only want InSpectrum in Linux, you can install it directly. Typically in Mac OS, it's accessible via Homebrew or Mac ports, but since you have Radio Conda, more likely you already have InSpectrum within your Radio Conda environment. So we can open one of these CGMF files. It doesn't matter which of them because the two of them are like logically linked. And there are sliders here to adjust some settings. So I'm going to adjust the FFT setting, for example, like so. And we can see, so the horizontal axis is time. We can see that recording duration is 5 seconds. And then the vertical axis is frequency, sorry. So we can see the span is from minus 100 kilohertz, which is on the bottom, to plus 100 kilohertz. And we can see this is the signal of the broadcast FM station. Maybe it's easier to see like this. But you can see how it's changing the pattern according to the voice or whatever which is being transmitted. So this is a good tool to look at recordings you might have for analysis or post-processing. You can scroll, and if this was a longer recording, it makes sense to scroll and maybe zoom into smaller portions of the data so we can see like this part of the recording, for example. There are other things related to signal analysis that can be done with InSpectrum. So I'll just show that if you right-click, there are ways to add plots. I will not even show the plots, but you can experiment with this on your own. So, okay, maybe any questions at this point?
No questions.
Okay, great. So we have a way of generating a Python script from within or from a GNU Radio flow graph. We have seen parameters end up corresponding to command line arguments. But then the thing we want to do is to actually call this flow graph from Python. And to show you how to call this from Python, I will show you how the Python code actually looks like. So I guess this is big enough. This is similar to, if you remember, like a month back at the beginning of these tutorials, I had a slide where I had some simplified Python code for a GNU Radio flow graph. This is just the same thing. So we have a bunch of import statements. All of this is automatically generated by GNU Radio. We have this class, which is our RTLSDR receiver flow graph. We can see the parameters are arguments of the class constructor. Then we can see the parameters are set here. The variables are calculated here. So for example, here we are calculating the number of integrations. For the FFT, that's the same formula we had entered in GNU Radio Companion. Then we have the blocks. So we are creating all the blocks. Each of them has their own options. And then there are the connections. So we are connecting pairs of blocks. Then we also have these get and set methods for each of the variables. They are not too important. For example, if we were to have GUI elements, this is what makes GUI elements function. But we also have this argument parser, which is the thing that actually gives us command line arguments. If you've ever used argument parser in Python, this is what it is. But finally, the thing which I care most about for this tutorial is this main function, which is the function that runs when we call the script. Because to call the flow graph from some other code, we want to do something fairly similar to what this main function is doing. So first, the main function is calling the argument parser to get the options. Then there's this top block class, which if you look at here, it's actually RTL-STR receiver flow graph that is called with all the options that have been parsed from the command line. And finally, this is not important. This is code that gets called when we press Control-C to stop the application. So not very important. If we ignore this, which is like setting up the signal handler to handle Control-C, then basically what we are doing is we are calling start and wait on the object that was returned by this top block. So that is how a GNU Radio flow graph is run from Python. We basically instantiate the flow graph, which is a Python class, and then call start and wait, or we call run, which is a combination of start and then wait. So that's what we are going to do from Jupyter. I will leave this in the background just in case it's useful. I'm going to fire up a Jupyter notebook. And I already have the notebook prepared because otherwise it would be me writing too much code in real time, which doesn't make sense. But I'm going to go through it slowly. So nothing unusual. We are declaring that we are going to be using matplotlib. We are going to be using pathlib, which is a Python built-in library for handling paths. We are going to be using NumPy and matplotlib. And then something new is from RTLSDR receiver flow graph, we are importing RTLSDR receiver flow graph. So what does this do? Because there is this Python file, which is called RTLSDR receiver flow graph in the same directory as the Jupyter notebook. So we can look at this here maybe. In the same directory, I have my Jupyter notebook and I have the Python file. This import statement is going to go into the Python file and it's going to import the object, which in this case is a class, which is called receiver RTLSDR receiver flow graph. So this is importing the class, all this code, basically. And then I basically have some settings to set the figure size. This is not too important. You can set the figure size of, to any size you want or leave it as a default. So how do we run the flow graph? We can call this RTLSDR receiver flow graph that we have imported from the RTLSDR receiver flow graph Python file. We can pass any number of arguments we want in here. And the rest of them, because they all have default values, will be left to their default. So in this case, I'm overriding the duration, just 3 seconds, and the output path is going to be temp, are you recording? So if I want to run this, then I can just click on this. And you can see it's basically the same thing as when we run this from the command line. We get all these printouts. We get this log which says we are generating this temp are recording. We can even check, is it there? Yes, it is. So there we have our new recording. So this is how we can run the flow graph a single time. Then, if you remember, there was this vector sync. So then the next question is how to access this vector sync from within the Python code. And then something which is important is every block within GNU Radio has an ID. They are hidden by default. So there is this show of block IDs. This can be changed. So in most cases, I have left the default names, which oftentimes come with a 0 because that's the way to distinguish if we have multiple of these blocks. But in here, because we are going to access this from Python, I have given it a specific name. So it's going to be called Spectrum Vector Sync. Then if we look at the Python code, you can see that there is a block in here, what it is here, which is called Spectrum Vector Sync, which is our vector sync. So we can access it like so. For example, if I run this cell, it says that flowgraph.spectrumVectorSync is a vector sync object, which is at this location in memory. The memory location is not important. The fact that Python knows that this is a vector sync is important. So there is documentation for the vector sync here, because the question is how to fetch the data. And you can actually see there is a Python example which says you might have something which is like top block, my vector sync, and then you call .data and you get the data in that way. So that's one way of figuring out how to call these things from Python. Another way is there is the header for the block. Because in this case, the documentation has the example we need, but it might not be in the documentation, so we might need to look in here. So this is a C++ header which defines what methods are public functions of the block. And in this case, there is a reset which clears everything that is stored by the block. There is this data which returns a vector of values. And then there is this tags. I'm probably not going to speak about tags in all the summer, but just so you know, sometimes it's useful to mark particular samples in a sample stream. They might correspond to specific events that have happened at that moment. And in GNU Radio, that's done with tags. So we basically insert a tag in a particular sample, and the tag can have some description or some numerical value. And that's the way of saying, hey, something happened at this point, right? It might be a detection, for example. Maybe you are trying to do, I don't know, fast radio burst detection, and you are trying to do it in real time. So you have some algorithm, and whenever it sees something that might be a fast radio burst, it puts a tag there which says, hey, here is a candidate for fast radio burst. And maybe it says the SNR is whatever number. It might be very large if it's a clear FRB, or it might be smaller if it's somewhat of a more dubious candidate. But then something downstream of that can be looking at the tags and say, okay, if this is an FRB candidate, I want to take some IQ data around this location and record it to disk for later analysis, or I don't know, I want to queue up other instruments or whatever. So that's what tags is about. We are not going to use them, but just so you know that they exist. So to get the data, we call this .data, and it returns a list of numbers. Not very surprising, it is storing numbers. So basically, every number that comes here is stored within the vector sync. We know that we are sending vectors of 64K points because those are our FFT lines. So then it makes sense to make an numpy array with this list of numbers, reshape it with however many rows we need to have, and an FFT, so that's 64K point columns. And in that way, we can see each of the FFTs that have been stored in this Spectrum Sync data. So we only get two FFTs. This is the shape. It's a matrix which is 2 rows, 64K columns. Why do we have two? The reason for that is I have set the duration to 3 seconds here. But the integration, I have tried to set it to 1 second, but because there is a rounding here, it's not exactly 1 second. It's slightly above 1 second. So in 3 seconds worth of data, we get only two integrations and one integration, which is almost complete, but since it's not fully complete, it's never written to the vector sync or the output. So that's the reason why we get two FFTs, and then we can plot each of them. So this is a very simple plot. And you can see this looks pretty much like the spectrum we were displaying in GNU Radio. What else? Just a small technical detail. If I try to run the flow graph again, for example, let me run this cell again, I will get an error, which is fail to open RTL-SDR device. This happens because our previous instance of the flow graph is still using the RTL-SDR stick. So unless we destroy the flow graph, and this is done by using delete in Python, so we delete the flow graph, we will not release access to the RTL-SDR, and then we couldn't run any other thing that needs the RTL-SDR. So that's the way to make the RTL-SDR usable again. So now I have deleted it, and I think I can run this again. Yes, so it has made a new recording. I can delete it. Sorry, I can delete it. And I can run it again, and I could run these cells as many times as I want. Each of the times is generating a new recording and also new spectrum that we can wrap like this. So this is slightly different from before, as you can notice. Okay, any questions at this point? Great. So we come to the final part of this part of the tutorial, which is we are going to make an example observation, quote unquote marks. And the reason why this is like a fake observation is because we don't have a radio telescope here. We are not going to be observing two different targets like you did last week with the Allen Telescope Array. We are going to be recording data on different frequencies. But that's like good enough for demonstration purposes. If you know how to do observations at different frequencies, then if I hand you a full-fledged telescope, for example, if I give you access again to the Allen Telescope Array and I tell you how to point the dishes and how to do the other things that need to be done, such as setting up LNAs, then you also know how to do all of these. So you could go through a list of targets like coordinates on the sky and collect data at each of them. It's just the same principle. So what do? We have a list of frequencies. These are center frequencies for the RTL-SDR. I have selected these by hand because I know there are signals of interest in each of these frequencies. I want to show you some interesting emitters also. Then this is the list of frequencies where I'm tuning my frequency translating FIR filter. So this thing. I basically know that within these frequency bands at these offsets, so for example, at 98.8 and at 95.8, there are transmitters of interest. And then decimations. So for each of the recordings, I'm using a different decimation because the signal I'm interested in has a different bandwidth. So I want to make sure that we capture all the signal in the output bandwidth. And finally, I'm using a duration of 10 seconds for all of them, but I could also have a list of durations and use a different duration for each of the things, or I could calculate it based on, I don't know what. You can see there's a lot of power with now doing things with Python. So we are going to be using a Python dictionary to collect all the spectrum data because we are going to plot it afterwards. We are going to create a new directory, /stem/observation. You can create it wherever you want. If you are on Windows, then this is probably not a valid location, but you can choose a valid location. So here we create that directory, and within that directory is where we are going to put all our IQ data files. So what we do now is basically we loop through the list of, well, basically through these lists. So for each R frequency, translating frequency, and decimation in my lists, we are going to print a message to be aware that this is running. We are going to select the file name for the output, which is going to be my output directory, and then slash IQ data, and I'm going to put underscore and the R frequency to have a different file name for each of them. You can use any naming scheme you want, and of course, observatories actually have like a standard naming schema for the data files, where usually you have like the timestamp in terms of the MJD. You might have the source, you might have a project ID, so you could format all of that in here. Then what else could we do? If this was a real observation here, we would move antennas, we would wait for them to reach the source. We might want to set up LNAs or whatever. Then we run the flow graph to collect data. We are passing all the parameters we have chosen here. So duration, the RF frequency, the frequency translating FIR filter frequency, the decimation, and the name of the output file. We run the flow graph. So this will collect data for 10 seconds. And then we grab the spectrum vector sync data, we reshape it as a NumPy array, and we store it in this Python dictionary classified by the RF frequency. And then, very important, we delete the flow graph. And because otherwise the next loop iteration is going to complain that the previous iteration has exclusive access of the RTL-SDR. So we delete the flow graph so that the RTL-SDR, so that the next iteration is able to access the RTL-SDR. So this is the observation. How many targets? 1, 2, 3, 4, 5, 6, 7. So 10 seconds observation for each of them. This will take slightly more than a minute. I'm going to kick it off now. So you can see the cell is running. We get receiving on 98 megahertz tuned to this thing. And it's going to be like this for 10 seconds. And after 10 seconds, we will print the next message, which says we are tuning to the second frequency, blah, blah, blah. So this is also a good moment to stop for questions. Okay. While we wait for this to finish, I ran this earlier yesterday, I think, when I was preparing this. And I can show you the results of my yesterday run, and then we can compare with this run. So spectrum data, once this loop finishes, so this is from yesterday, is a Python dictionary classified by frequency of two-dimensional arrays that have 9 entries. Again, 9 because we are doing 10 seconds, 1 point something seconds per integration. So we only get 9 full integrations in our data. And then 64K because that's the FFT size I have. So a whole bunch of numbers. It's very difficult to make any meaning of these numbers unless we plot them. So to plot them, nothing very interesting. This is just like some NumPy code. I'm not going to stop. You've probably seen some things very similar to this. So let me show you what I got yesterday. What I got was, for example, at 98 megahertz, there are some FM stations. This is the thing we were looking at before. And we can see this is the waterfall. So this shows how they change over time. This is just the spectrum. So we don't have the time component here. Another set of FM radio stations at 95.5 megahertz. So that's another FM station. Then 117.5 megahertz. You can see there is RFI. There is a bunch of RFI, but there is a signal here. It's better seen on the spectrum. We will take a closer look at this signal. It is an air traffic navigation signal that airplanes use to figure out where they need to go. And that's called VOR, which means VHF omnidirectional ranging, I guess. So then another one, this is worldwide. So in the States, you will also get VOR stations within the same frequency range. 400 megahertz, around 400 megahertz. This is more frequent in Europe than in the US. There is a service called Tetra, which is a handheld digital radio service. The police, the fire stations, ambulances, they use these radios. So you can see here there are 2 Tetra stations and lots of RFI because I'm not in a great location. What else? 800 megahertz. We have a narrowband LTE signal. This is 4G cell phone signals and 2 like full LTE signals. These LTE signals are 10 megahertz wide, so they don't fit within the RTL-SDR bandwidth, but this one fits. I think I showed this on the first day. The more cellular signals, so 935, this is a GSM signal. So this is the first and second generation of cellular technology. Another type of signal. You can see the spectrum shape is different. For example, this is like more rectangular and this is like smoother. It's actually like supposed to be like a Gaussian. And then we also have an LTE signal, which doesn't fit on the spectrum we are sampling. And finally, it's very difficult or impossible to see here, but we will see in spectrum. 1090 megahertz is a frequency for something called ADSB, which are airplane position reports. I think I also mentioned that, but if you have seen any of these air traffic maps on the internet, they use this signal. So there are receivers on the ground which receive these beacons from airplanes that transmit the airplane GPS coordinates, and that's how we get those maps. So with an RTL-SDR stick, you can make your own map based on signals you receive. There are open source applications for that. You can just download, install, and run if you are interested. Okay, so that's what I recorded yesterday. Now this has finished, so we can go through the log. We can see that it has run for all of them. And we can evaluate this again. We will get different numbers. And we can evaluate this again. And you can see that the plots are slightly different because, well, the FM radio stations, depending on what kind of music they are playing, the spectrum will look different. So this one definitely looks different. This also is pretty nice shape. Okay, that one's nice. For example, one of these was weaker. Also, there's some difference. Now my RTL-SDR stick and the antenna are on my table. Yesterday, I was like holding it up in the air to hopefully get a better signal. But this is pretty good, actually. I'm happy with the signal quality here. So you can see many of these signals are like present all the time because they are services which run continuously. Some others might not be present all the time. Questions at this point? Okay, let's look at some of these files in Spectrum. For example, I want to show you this 425, which is the Tetra handheld radio. There is a lot of interference or saturation or something. These vertical lines are unexpected. But you can see the signal is in the middle. It's fairly strong. And then there is also a much weaker signal of similar characteristics, which I don't know if we could see in here. Presumably we could. Maybe it's like hidden. It should be right there. So that's one example of something you can look at within Spectrum. The other one I want to show you is the 1090 megahertz. I don't know if we will be able to see anything. Yeah, but it's like very weak. So If you bear with me, I don't know if the screen share quality is good enough for you to see, but you can see there are like some small pulses in here. So those are the aircraft signals I was talking about. And because this was on my table, the signals are not going to be great. I am indoors, but yeah, you can see a bunch of these aircraft signals, and some of them contain the position reports. There aren't any which are like strong enough that I can show you how it actually works, but that's enough really. Okay, yeah, I think that's it for this part of today's tutorial. So we can take a 5-minute break now. And then the next part will be about how to write simple blocks in Python. So we will be writing our own signal processing code in Python for GNU Radio to run it.
Not yet. We should probably just get started.
Okay,
Yeah,
I think we can get started. She will catch up. So yeah, I'm sharing screen already. I'm going to cover these Python blocks. So the example I'm going to talk about is spectral kurtosis calculation. Depending on what you are doing for your summer project, you might already be working with kurtosis or something related. If you are not familiar with kurtosis, the only thing you need to know is that it is a statistical quantity which can be used to distinguish random variables which are normal from or Gaussian from random variables which are not Gaussian or not normal. And the reason why it's very useful for us is as a mechanism to detect interference, because noise is usually Gaussian and interference is usually not. So if we have this statistical quantity that can give us different values depending on how Gaussian something is, that can be useful to tell, hey, these signals do not look like Gaussian variables, so they are probably interference. So that's what kurtosis is, and the term spectral just means that we are going to apply it to the spectrum. So we are going to apply it after doing an FFT to pass to the frequency domain. There are slightly different definitions of kurtosis out in the wild. I'm going to use the one from this linked paper, which I think it's a pretty good introduction also. So if you want to read the full paper, it's a good read. And the formula is here. So I'm going to explain the notation for you. Basically, we have a signal which we have already performed the DFT, that is the Fourier transform. So we have already performed the endpoint fast Fourier transform. And this gives us vectors xi. So I is the frequency bin. I don't know why it says, no, sorry, m is the frequency bin. So m goes from 1 to n. And then because we do this over time, we basically get a sequence of vectors. So that's where I comes from. We get essentially a list of these endpoint vectors. And then to compute one of these kurtosis, we need m. So that's this other number m time steps to perform the statistics. That's where the index I comes in play. And the statistic we compute is computed independently for each of the Fourier bins. So you can see the M, which is the FFT bin, is in here, in here, in here. And we basically grab the complex numbers in the FFT. We compute the sum of the squares. There are modulus, so these are all real numbers, positive real numbers. We square it. So this is like square, sum, square. And we compare that with the sum of 4 powers. So rather than square, sum, square, you can think about this like square, square, sum. So that's what's going on really, and that really gives you different results depending on what's like the distribution of these random variables. And then a whole bunch of normalization parameters. And the goal of these parameters is that we get something that is centered at 0 for something which is Gaussian. This whole thing is to give you an unbiased estimator. we need not worry about it. So this is the formula we want to write in GNU Radio. Any questions about the formula or what kurtosis is about? As I said, there are slightly different definitions of kurtosis out in the wild. So maybe if you are doing a project that uses kurtosis, you are using a slightly different formula. That doesn't matter. You could use a different formula in GNU Radio also if you want. We are going to be writing this in Python. So you have all the flexibility. Okay, so if we go to GNU Radio Companion, there's a whole solution here, but I've started already by the basic parts of the flow graph, which is again and again the same thing, RTL SDR source, frequency sync, so that we can see these signals. And if I run this, just to make sure that it runs, nothing new. We have our FM radio stations, and hopefully in the kurtosis, we will be able to distinguish these from the noise floor. So that's what we expect. Then what do we need for kurtosis? Well, the first thing we need to do is an FFT, right? Because it's supposed to be spectral kurtosis. So I'm going to do 1024 point FFT. That's not critical. It depends on how much frequency resolution you want to use. And then the same thing as always. So stream to vector, single stream to vector. These are complex. The size is NFFT. And then FFT. And I see in the example I had 4096. So for the sake of consistency, let's stick with 4096. So NFFT, NFFT here. And this is what is generating our vectors xi. So now we want to have a new block, which is a custom block that we are going to write in Python that makes this calculation with the xi's that would be at the input. So if we search for Python, we can see that there is Python block, Python module, Python snippet. And the thing we want is a Python block. So this is called embedded Python block. The way this works is quite simple. So we double click on the block, and then there is the code. For the code, it's going to be Python code. So there is the option of opening it in an editor. And we can also choose an editor. Sometimes people have issues choosing an editor. It depends on the operating system. In particular on Windows, it's like difficult. But this should work one way or another. Reach out to me if you find issues in your operating system. You should be able to choose a text editor and then open your code in an editor. So let me get this window out of the way. And then this is my editor. And this is the code we get, which is a template that we are supposed to modify to put in here our signal processing implementation. And there are lots of comments with documentation. So the first thing I'm going to change is the name because it says this will show up in GRC. So I'm going to put here spectral kurtosis. And whenever I save, you can see that the GNU Radio Companion window has updated in real time. So now my blog is called spectral kurtosis. That's great. Now what happens? Well, in the input, we want to put these vectors of 4096 elements, but this is like a light blue. If I try to connect, I cannot try to connect them with the block open, but bear with me. So I need to specify here that the input signal is a vector of 4096 points rather than a single complex number. And the way to do that is just this in notation. If we do a tuple of a type and then a number of elements, that's how we specify that the input is a vector. So we can do that, and then we can see this is dark blue, which means it is a vector that we will be able to connect here. Then what happens with the output? Well, we need to change two things about the output. The first thing is it also needs to be a vector. So let's do that already. We know how to do that. So now it's going to be a vector of 4096 points. But now let's look at the formula. This is a real number because we are taking modulus. So all of these is going to be real. So we want the output to be real. And then these are NumPy types. So it's nothing specific to GNU Radio. Float 32. That is the real data type. So now we can see this is brown. It's supposed to be dark orange, which means real or floating point. So, okay, we have now set up the types of our block correctly. What else do we need as parameters? Well, there is one parameter which is quite clear here, which is m. This is like the number of vectors that we are going to use to compute an estimate. So let's put it like that. M equals 10, and it says only default arguments here, which means you need to specify a default argument. Okay, so we have m. Then what else is important here? It is important to notice something else. We use m of these vectors as input, but we produce only one output vector, that is. So if we are calculating kurtosis continuously over time, we would take the first m vectors, compute a single kurtosis vector, then take the next m vectors, compute the next kurtosis vector, then take the next, you follow it. So this is actually applying a decimation by m. We have m fewer vectors at the output than at the input. We need to tell GNU Radio that. GNU Radio needs to be aware that this block is decimating. And the way to do that is with the block type. So here it says there are other base classes like basic block, decimating block, and interpolating block. And decimating block is the block that we are going to use. So we are going to change this into a decimating block. Because we are changing the parent class here, we also need to change the parent class there. This might seem a little bit too technical, but I'm fairly sure Claude knows how to do it. And also there is documentation. So if you search for GNU Radio Python block, there is this embedded Python block documentation that might contain some interesting examples, but there is also a whole tutorial on how to create your first Python block. So this goes through all the explanations I'm going today and maybe even more. For example, it explains to you how you can have multiple input ports, which I'm not demonstrating today because I don't need it. It's basically you use the list of inputs. So all of this is documented. That means do not worry about technical details like whether you need to match this decimating block and in here and here. So we have this decimating block. Also, there's a comment here which says if an attribute with the same name as a parameter is found, a callback is registered. Properties work too. So let's do that. Why not? We actually need to store it. This value m, it will be useful to store it. So we store it as m. And then what else? Yeah. So I'm actually going to do something. Well, I'm actually going to put it here. Self NFFT. Let's remember that we are using 4096 FFT points. Why don't I set a parameter here? The reason is that it doesn't work properly with the type definitions. I could set something like NFFT equals 4096 points here, then use NFFT right there, but this doesn't work for silly technical reasons. So that's the reason I'm avoiding it to set here. It's slightly inconvenient. It means if we change our 50 size, we also need to go to this code and change it, but that's fine. Okay, then you can see that the example that we are given is multiply all the input by a constant. So there was this example parameter, and we have our input items 0. We have this 0 because it's the input port number 0. In this case, we only have one input port. So this input port, if we had multiples, then we would have input items 0, input items 1, etc. And then everything in output items is going to be overwritten by input items multiplied by the constant. And finally, when we are done, we need to tell GNU Radio how many items we have produced. And in simple cases such as this one, it's just the length of the output item. So we need to tell him, hey, we have written however many numbers of elements here. So this value. Let me show this window again. So this is showing some errors. This will show errors whenever your Python code is not correct and things will be in red. It says, for example, can't create an instance of your block. Decimation is missing one required positional argument, decim. Oh, that's interesting. It means that I have forgotten to specify in here that the decimation is m. So now if I pull this window again, we can see that this is no longer has any errors. I'm going to use 10. I think I have 10 in here. No, I actually have a calculation. So let me grab the calculation and then put it here. So what's this calculation? It's basically we want to generate one kurtosis estimate per second. So we are dividing the sample rate by NFFT, and then that is the number of FFTs we have per second. So we are going to aggregate all of them into a single spectral kurtosis estimate. We could try different values and see how the accuracy of the estimate changes. Of course, the higher you set the n value, the more accurate that the estimate will be, but the longer it will take to respond to changes in the signal. So, okay, this spectral kurtosis is now, it's not doing anything because, in fact, it will fail if we run it because this doesn't exist. But let's connect it to something so that we can run it and check that it fails. The rest of this is fairly straightforward, so I'm going to copy and paste it. It's just the repeat trick because we are only generating one vector output per second. So if we want to display it, it's good to repeat it. And then we have the usual vector sync where we have set the values of the axis appropriately to display the frequency scale in megahertz. So if I run this, it will crash. At some point, yeah, it has crashed. And then there are O's, so I need to close this. So you can see there's an error here. It says attribute error, object has no attribute example param. And we actually get a line number. So you can see this is Python blocks demo 2, blah, blah, blah. This is our Python code. It's line 32. So if I go here to line 32, you can see this is line 32. So this is how you find your mistakes. You will get like the error here, and then you can go to the line and figure out what's wrong with that. So example parameter doesn't exist. That makes sense. We have removed it from here. And we need to change this and to actually write the formula. So that's what I'm going to do next. But before that, any questions? Okay, so what do I write in here? Well, M is important, so because it appears a bunch of times in the formula, you can see it's in 3 different places. I'm going to save myself some typing by making this assignment. And then I'm going to essentially this xi, I'm going to call it x in here. And this is going to be input item 0, but I'm going to reshape it in the following way. So whenever my work function gets called, it's going to be called with some number of input items. We don't control how many because GNU Radio calls the work function as often as it deems necessary. And that means that already a lot of input might have accumulated, or there might be little input because GNU Radio is calling work again and again and again. It basically figures out when to call work for us. So that means that generally speaking, the amount of data we receive into work is unknown and variable, but generally that doesn't matter. It only means that we need to adapt our processing to the size of the input items we get. This should be input items. So I'm reshaping it like this because I don't know how much data I have in total, but I know that I want to have blocks of n vectors, and each of the vectors is going to have size nft. So I might only get one of these blocks, I might get 30 of these blocks, it doesn't matter. I'm going to do the same calculation block by block. I'm guaranteed to get an integer number of blocks of n vectors because this is a decimating block. So if I have said that we are decimating by m, and I have said it here, then the amount of elements we get in here is going to be a multiple of m. It could be m, it could be 1,000 times m. So that's why I have this -1. So I'm going to do something so that you can see. I know this is still going to fail because I haven't changed anything about this line, but I want to show you how this reshape works. Maybe I'm going to cheat. I'm going to comment this line. So we are not going to write anything on the output. We are just going to pretend we are producing output. Whatever data is already on the output will stay there. But then we will be able to see that this is printing a bunch of things. So you can see it always seems to be called with one block of 781 vectors of 4,096 points. But that's just because this m is large. If I set a smaller m, maybe we get a different arrangement. Let's see. 178. Okay, so no difference. Maybe let's do something smaller. What happens if I call it with 8? I'm also getting one block every time, but that need not be the case. If I had a larger sample rate or who knows what, we might get multiple blocks. So the lesson I want to make clear with this is we cannot rely on the size of the input. The only thing we can rely is the output size is going to be the one corresponding to the input size. So in this case, it's going to be m times less output elements than in the input. But we cannot rely in general how many input items we will get. Okay, so that's how my input looks like. And then we are going to compute the kurtosis. I'm going to rearrange windows so that we can see both things at the same time. Because I'm basically going to copy this formula. Because this x to the power 2 appears a couple times, I'm going to compute it. So this is x, the real part to the power 2, x imaginary part to the power 2. So this power is the power 2 we have in here. So then what we can do is, for example, let's write it like this. M divided by m minus 1 multiplies, and then in here I have m plus 1, and then I need to sum the power 4. So the power 4 is this power I already have to the power 2. And my axis needs to be the m axis. So that is axis 1. The other axes of this matrix, I need to leave them alone. So I'm basically collapsing everything along this m dimension. So that's the thing on the denominator. I'm realizing we don't need so many parentheses. Then we can divide by, there is a sum of power axis 1, and this has a square in here. So that's what we have there, and then there is a minus 2. So I think that's correct. Let's look at it again. So I have this quotient. I think I'm missing a closing parenthesis. Yeah, that's right. So I have this quotient at the beginning, m divided by m minus 1, then big parentheses. Okay, that's my big parentheses. Then on top of the fraction, I have m plus 1 multiplied by the summation of power squared. Remember that this is already squared, so that's how we get the fourth power. Axis 1, and then divided by, we do a sum, and then do the square of the sum. So that's the thing we have in here. And then there is a minus 2, which has less precedence than the division. All right. Any questions about this calculation?
No questions.
Excellent. This is all NumPy matrix operation, so you can figure this out for any other calculation you need to do. And finally, we assign output items equals this kurtosis calculation. So that's the Python code we have for our block. And now we can try running it. I don't know if I have made mistakes or not. Sometimes I make mistakes. It's even more interesting if I make mistakes because we see how to solve them. But I'm afraid I haven't made any mistakes. Well, the mistakes I made at the beginning are enough of an example of what happens if there are mistakes. So if there are mistakes, you get an error here, the execution stops, and then based on the error, you can go back to the code and try to fix it. So, okay, our spectral kurtosis is working. We have the spectral kurtosis displayed here, and we get values across the spectrum. So this is the power spectrum. This corresponds to power. This corresponds to kurtosis. As I mentioned before, I have done something wrong because this is not centered at 0. Let's look again at the formula. And I have one that was working fine. Yeah, I think I have the same formula in my example, which I tested yesterday. Let me compare the two of them real quick. Yeah, they look identical to me. So I'm now realizing that this is around 2 point something. I'm going to do something. I'm going to remove the antenna to see what happens. Okay, interesting. So this is centered on 2. There is definitely something wrong with the normalization. I don't want to waste too much time figuring this out. Maybe it's this thing about precedence. I don't know. I'll figure it out what's going on offline and tell you, but it's surely a stupid mistake I have made with one of these formulas. Surely it must be that. The M is correct and everything. It's just only a matter of, and I have the minus 2, it's only a matter of centering things. So what I'm noticing is when I have only noise, which is now I have the antenna disconnected, The spectral kurtosis should be centered at 0 rather than at 2, but we have a small bug. I will fix it all offline unless one of you already has realized where I made a mistake. Doesn't matter so much for what I want to explain right now, which is basically how the kurtosis works in practice. So forgetting for a second about that normalization thing, the noise floor, because it's Gaussian, is going to sit at this constant value, and any kind of interference, such as our FM stations, which doesn't look like a Gaussian, will show up in the kurtosis. And you can already see some very useful features of the kurtosis. For example, there are some very weak stations here that are not so easy to see. But on the kurtosis, for example, this one is quite prominent. So it is a sensitive detector to some kinds of interference, which are not easily seen on just the power spectrum. So that's one of the useful things about kurtosis. You can also see like there are some spectral lines that keep appearing. Those are like small interference blips that are so small that they don't register quite well in the power spectrum, but they show up in the kurtosis very well. So this is an example about some kind of signals that appear in the kurtosis, but there are other examples of other signals that appear in a different way. So for example, I think I've probably crashed these by, yeah. I shouldn't have done that because I put an empty value in that and I crashed the flow graph in that way. If you remember, there was this VOR aircraft navigation signal at 117.5. 117.5. And maybe I need to hold this up so that we can see it. 117.5 megahertz. Sorry, I forgot the megahertz. And I don't really need to hold it up. Okay, so the signal is here. We can look at it there. I realize I haven't showed the signaling in Spectrum where it's easier to see. I will show it in a second. But something I want you to notice is that the kurtosis is actually negative. So this is the carrier of the signal. This is supposed to be 0. I know it's centered on 2. That's a bug we need to fix. And this is below. It's supposed to be -1. So this is because this is a CW tone. It's a wave which has constant frequency and amplitude. And that's how those signals show up in the kurtosis. They have kurtosis -1. So not all the interference has positive kurtosis. There are things which have negative kurtosis, like this one. So that's a good example. Because I wanted to show this in, let me show it in Spectrum. That was temp observation, IQ data, 117.5, CMF data. So this is the aircraft navigation signal, and what we have in the middle is this this CW carrier, which is basically constant amplitude. We have this. This is actually frequency modulated sidebands, which is how the airplane knows the radial in which it is. That is the bearing from the ground station to the aircraft, and that's how it figures out where to fly to. And then it's kind of weak, or probably it's short. This recording is too short, but this is sending Morse code identification every now and then. So we should be able to see, it's maybe these lines. Yeah, I think these weak lines are the Morse code identification. So that's how the signal looks like. And that's the reason why we see this as negative in the kurtosis. What else? Let me see. Other interference sources. I want to show you more of these. So there's a reason I showed this signal besides the fact that it's strong. So this is at 4 to 5 megahertz. So you can see it here. It's interesting. It doesn't look, yeah. Okay, so something to notice is actually the kurtosis on the signal itself is pretty close to 2 in this case, or to 0. It's pretty close to the one in the noise floor. We get these things on the sides probably because there is like interference. Maybe the signal is too strong and I need to lower the gain or something like that. But for example, this other signal, which we can see quite easily at 1 megahertz on the spectrum, it is very difficult to see here. The only sign of it in the kurtosis is this little point. You can maybe see it more easily like that. So this is a good example that there are some interference signals. So there are some communication signals that have very similar statistical properties which are very similar to Gaussian noise. For example, this case of a tetrastation. And so the kurtosis is not a great way to detect these signals as interference. You have an example here. In here, it's very easy to see that there is a thing here, and it's very difficult to see it here. And I promise when I did the same thing yesterday on this station, this was all flat. There weren't these weird things. So there might be something special going on today. So that's an example of a signal which is very difficult to see in the kurtosis. Just so you know it, that's the reason why there are different tools to detect things, because there are different things to detect, and some show up better in some of the tools or algorithms than in others. Let's look at these aircraft signals. I'm going to hold up the RTL-SDR dongle. So this is an example of something which is the opposite. It is much easier to detect in the kurtosis. You can see there are blips appearing almost always. It depends on what airplanes are flying and transmitting right now. But because these are very short pulses, it is difficult to see them on the power spectrum. But it is very easy to see them on the spectral kurtosis. The kurtosis is really well suited to detect signals which are short pulses, because it is doing statistics to try to detect if something is Gaussian. And one key property about Gaussian distributions is that they don't have many outliers. However, if you have a signal which is a short pulse, when the signal is on, you will have some values, a few values which have a large value, and then you have the rest of the values will have a much smaller value. So that's a lot of outliers, and then this calculation of the kurtosis will pick them up. Essentially, what happens is that because there is the power 4, the outliers greatly increase the number we have in the numerator in comparison with the denominator. So yeah, that's an example of signals, like short signals. Radars is also another example of short signals, where kurtosis is pretty good at detecting these things. Maybe just for fun, let's check the other thing that was 801 megahertz. So these cellular signals, these can both be detected fairly easily in the spectrum and also in the kurtosis. You can see, for example, here, that one is pretty easy to see in the spectrum, but also in the kurtosis, we can see here is some interference. Here there is just noise between some of the cell stations. Here there is also just noise, and here there is another station. So if I auto-scale on this one, you can see similar detection capabilities on the two plots. It also kind of depends on what data is being transmitted. For example, you can see this station is not showing up as clearly in the kurtosis as this one. But there you have it. So there you have one tool to detect interference. Also, I think this illustrates the beauty of prototyping signal processing algorithms in GNU Radio fairly well, because we have written just a little bit of Python code, and suddenly we are able to uh, get it running in real time with hardware and look at different signals, look how it works. So you could go through the paper if you want to understand how the kurtosis works. And it has some examples, it says, for example, there is this example signal, and then the kurtosis is 0. So essentially, if it's noise or noise-like, the kurtosis is 0. Then if we have a CW carrier, which is the thing I demonstrated with the VOR station, the kurtosis is -1. And then what happens if there are both of them? So the kurtosis depends on the signal to noise ratio. What happens with non-stationary signals? So that's the aircraft signals, which are short pulses. It comes up with this positive quantity, and then it has some examples and some example plots. But at least for me, this is so much more intuitive. You can point your SDR at different signals and see in real time how the math works and what output it gives. So that's really an advantage of doing this in GNU Radio, and I think it's not too difficult, especially if the signal processing algorithm is as simple as a single formula, which is not always the case. There are some algorithms which are more complex. Okay, questions at this point? Okay, so that's basically all I have today. Just because I have this worry about the normalization of the kurtosis, I'm going to execute the main flow graph I have, and that's also not normalized properly. I think. Let me. Well, the easiest way to figure out is to unplug. No, this one is actually normalized properly at 0. So what's the difference then? It might be some slight mistake I made in the formula. Where do I have my formula? I think it's identical. I don't see. I'm comparing just so that you don't wonder what I have done is in another window I have opened this thing, and maybe that is a good way to show it. So let me put this over here.
Have you got a bracket missing there at the open parentheses at the beginning?
Oh, yes, that's different. Why does it matter though? This bracket is the same as this one. Oh, yeah, I see what's the. No, so I do have a bracket here, which I don't have in there, but that shouldn't matter because this multiplication also goes on top. So it's like m divided by m minus 1 and then multiplied by the rest. So this bracket does nothing because of operator priority. But I now see the problem with this one, which is that look at these brackets. This -2 has gone to the denominator because my brackets are wrong. Compare, I don't have the brackets there. So that's the mistake I did. If you go back to the original formula, this -2 needs to go outside the fraction. And that's really what I need. If I, like this is my fraction, m plus 1 multiplied by this sum divided by this sum. And then that's it. And besides the fraction, I have this -2. Okay, so now I can close this. This is the one we were editing. And I think I can run this again. And I'm with the antenna disconnected, and now I get the right normalization as 0. and now everything works. So yeah. Maybe that's the reason why we got some slightly weird results with the 425 megahertz signal. So let's check that out again. It's also similar. It also has these funny things to the sides. But now you can see it's nicely normalized at 0. So, okay, as I said, I usually make mistakes. So that was a good mistake to try to see what's different and where the mistake could be. Any other questions or remarks?